Hi guys, in this video we're going to continue to look at the graphs of polynomial functions. Specifically, we'd like to sketch them. And so, because this is a very set in stone process, I want you to just kind of see these steps again a couple times. So we're going to take a look first of all at this third degree polynomial that you see over here on the left, this first polynomial here. And so the first thing we always tend to do is to deduce the end behavior of our graph based on the leading coefficient test. And so our leading coefficient, looking at this, is a positive 2 here. And so what that does is it tells us that the right-hand side of the graph has to rise. And furthermore, because our degree is odd, we have an odd degree here, the left side would have to do the exact opposite behavior, so it's on the right. So it's falling on the left, rising on the right. And we're actually going to write this formula formally here. And so we're going to say as x goes to negative infinity, as our x values go to the left, our y values, or f of x values, look like they're approaching negative infinity. And as x goes to the right, as x approaches positive infinity, our f of x values in this particular case are also approaching positive infinity. So we have our end behavior here, and that's just going to mean that when we do actually end up making our sketch here, we know that the right-hand side of the graph is going to rise and that the left-hand side of the graph is going to fall. Now, besides end behavior, what else do we find? Well, we tend to always find the zeros. We always want to know where it hits the x-axis. And so to find zeros, remember, these are the x values that when we plug them into this expression, we get 0 for a y value. So another way to interpret this are the x-intercepts. So to find these, let's go ahead and substitute in a 0 for our f of x value here, and we're going to solve this most typically by factoring. And so in this case, and in every case, we always check for a GCF first when we do factor. I notice that both of these terms have a 2 and an x squared in common. So what we end up with out in front is 2x squared. And on the inside, we would get left with just x minus 3. Now, examining this one, which we should do, I notice it has 2 terms and it's a difference, but it's not a difference of 2 squares, and nor is it a difference of 2 cubes. So this is a prime factor and we're done factoring. So the rule was, or is, whenever we are done factoring and have set this equal to 0, we're going to set our factors individually equal to 0 and solve them. So either 2x squared equals 0 or x minus 3 equals 0. Now one thing I want to comment on is that over here we get 3 for an answer, but we only get 3 for an answer once because this was this factor to the first power. It wasn't a repeated factor. But a fun fact about this factor here, 2x squared equals 0. If we set x squared equal to 0 and take a square root of both sides, we actually get 2 answers here. We get 0 positive and 0 negative, which are still both neutral, but I want you to notice that we have to have 3 real solutions in this case, or that we did have 3 real solutions, and that one of them is repeated. So with respect to our zeros, we're going to write 0 with a multiplicity of 2, and we're going to write 3. So that means that when we make this graph here, I'm going to go 1, 2, 3, 4, 5. We'll go by 1, 3, 4, 5. We'll go by 1 on our x-axis. That means that it hits at 0, and that it also hits at x value of 3. And so we know that we have this graph that kind of comes up and hits this dot, and then has to go through this other dot right here and end up. Now how it does this, how does it do this without crossing through another 0 in between 0 and 3? The fact is, because we got this with an even multiplicity, it means that at 0, it's going to touch and turn. But it's not going to cross the x-axis. Anytime we have an odd multiplicity, like it happened once, it's going to cross it at 0. So I can already imagine that this is some smooth curve that starts falling on the left, going and rising, increasing, and it touches and turns at 0 here, turns around, and then goes back up through and crosses at 3. All we need to do now is really just generate a list of values here, or a table of values, in order to get some more points on our graph. So here was the rule. Once we get the end behavior and we get the zeros, we are going to plug in some extra x values. And the thing here is you can plug in whatever x values you want. So as long as you're hitting x values to the left and to the right of every 0 will be good. I'm inclined to plug in -1 because it's to the left of our first 0. I'm going to plug in +1 because it's to the right of our first 0. Now this second 0 to the left of it is 2. I'm inclined to plug that in. I'm also inclined to plug in 4. And this is a good I guess, core set of x values we can start by plugging in here. And so if we were to evaluate these, 2 times -1 to the third minus 6 times -1 squared, what we get is 2 times -1 to the third. -1 to the third is -1. So we get 2 times -1 minus 6 times -1 squared is 1. Looks like we get -2 minus 6, which is -8. I'm going to box this. Now plugging in 1, 2 times 1 cubed minus 6 times 1 squared. 1 to any power is itself, and anything times 1 is itself. So in this case, we get 2 times 1 minus 6 times 1 is really 2 minus 6 is negative 4. So I'm going to box this as well. Now at 2, we start to get some larger values. 2 times 2 cubed minus 6 times 2 squared looks like we get 2 times 8 minus 6 times 4, which comes out to be a 16 minus a 24. We get a negative 8 here, so we're going to box this. And then at 4, looks like we're going to get 2 times 4 cubed minus 6 times 4 squared, which comes out to be 2 times 4 times 4 times 4 is 64. And then 6 minus 6 times 4 squared is 16 here. And so I'm actually going to write this out. We say 128 minus 60 plus 36 is 96. Looks like we would have 32 would be our difference here, 32. And so now what I want to do is kind of look at graphing these points. It looks like we're going to probably have to change the scale on our y-axis in order to accommodate, say, a 32. And so if we were to do something like that, maybe I would want to go by, I don't know, 5s. I could get away with going by 5. So we say 5, 10, 15, 20. And we're going to make this one bigger and call it 25. So we got 30, 35 right there. And we'll go negative also. Negative 5, negative 10, negative 15, negative 20, negative 25, negative 30, negative 35. So we got this change scale on our y-axis. If we go graph these now, negative 1 comma negative 8 would be left 1 and down almost 10. It'd be about right here. If we go right 1 and down 4, it'd be right 1 and down almost 5. So a little bit before it. We go right 2 and down 8. So right 2 and down 8 would be about the same height as what we were at when x equaled negative 1. And then right 4 up 32 would be right 4, but then up 30, and then a little bit more would be about right here. And so with what I can see, I feel confident that I can sketch a curve from left to right through this, a smooth curve that goes through these. The only thing I might consider is maybe plug in negative 2 just to see what height we would be at there. So 2 times negative 2 cubed minus 6 times negative 2 squared would be equal to 2 times negative 8. But this would be minus 6 times a negative 2. Negative 6 times a negative 2, which would be a positive 12. And so we get a negative 16 plus 12 is a negative 4. If I'm counting correctly here, let me check my math again here. Nope, sorry. This is 2 squared right here. And so let me actually just delete this out if I can do my arithmetic properly here. This is negative 6 times negative 2 squared, which is negative 6 times 4. So what we end up with is negative 16 plus a negative 24. This actually gives us a negative 40, which is a lot more reasonable. And so this other dot to the left of this would actually be nearly off of our grid. We would get something that looks like this. It comes up and touches and turns, doesn't cross, but then crosses at 3. I'm trying to do this in pieces here. And so we get this graph that looks like this, which in this case looks like it has a domain of all real numbers and a range of all real numbers. So you can see how putting all these pieces together, it's easy to come up with a graph for these. So those are the same steps we're going to take in nearly all of our polynomial sketches.